This call is now being recorded.
So, am I audible?
Yes, sir, you are audible, sir.
Okay. Yeah, so let's start with this Grover search algorithm today. So, yeah, so we'll mainly go through the first, we'll go through the motivation part. So, what's the motivation behind this Grover search algorithm? And then we will see the exact Grover's algorithm, what is that? And then we will see the circuit part, how the Grover circuit looks like. And then we will see the cascade implementation of the Grover's algorithm. So yeah, the motivation of this Grover's algorithm. So the Grover's algorithm is basically for the unstructured search. So unstructured means like in your list or in your database, we don't have any structure. It's in completely disordered way. It's listed in a disordered way. So for example, here, if you consider the list here, the details of, let's say, a database is a company database is there, and it has the details of, let's say, 2 raised to n employees. So why we have this 2 raised to n, that we will discuss later. But let's say for the time being, we assume that total number of employees is some 2 raised to n, and it's completely in a disordered way. So for example, if you see the first name, it's not in alphabetical order. So you have W before, let's say, S or P or J. Even if you see the last name, there is no order. The position, there is no order. Company, there is no order. But we have given a task that we have to find details of a company employee uh, whose name is Wendy Lane. So what the basic idea that we have, that we can pursue, is we can start from the beginning, and then we can go downwards, and then we will search that, okay, where we will find the name, first name Wendy. So we find here, then we'll search for the last name, then we'll search for the position, then we'll search for the company. So this is one of the example of unstructured search. So you start from the beginning, and then you have to trace uh, till the end until you get uh, the name Wendy Lane. And in the worst case, it may happen that the name which you are finding is at the end of the database. So we have to search for whole database. We have to search the whole database. So that is the 2 raised to n employees. The second example here is, let's say, finding the shortest path between two cities. So there are a lot of shortest path that can be like available between two cities, which is, let's say, here given, for example, two cities, Ann Arbor and Detroit. So we have a lot of combinations that can be made. So suppose for the time being, we have again 2 raised to n, that is kind of like exponential number of paths. So I have used 2 raised to n just to emphasize that we have exponential number of items in the list. So here we have exponential number of employees. Here we have exponential number of paths. And the task is the same, that we have to find the shortest path, that we have to find only one elements in that list, unstructured lists. So the naive method is again the same thing. You calculate the distance for each of the possible paths, and then you say, okay, this one is the minimum. But that one is the naive method, the brute force. So this can be actually mathematically formulated in such a way that, let's say, you have x1 till xn are the n variables, which take only positive values between the 0 to m minus 1. And what we have to find is, we have to find that which combination of this summation of xi's is equals to delta. And here the number of possible combinations. So we have this exponential combinations. So exponential number of possibilities we have. So here we have x1, x2, x3, xn, and all can take m values. So each x size can take m values. So there will be total number of possible combinations will be m raised to n, that is exponential. So yeah, the naive approach which we just discussed is we will define a function that is this p of x where it takes the combination of xi's, and this one is nothing but the summation of xi's. So if we multiply, this one is a vector 1, and then this one is also a vector x bar. So x bar here is represented just as a vector x1, x2 up to xn, and then 1 is a vector which all has ones, and this size is 1 cross n. So with this one is actually transpose here. So if we take this dot product, so then we'll get the summation of xi minus delta. So what we have to find is the possible set of this x bar, that is the combination of this x1, x2, x3, xn, such that we'll get the p of x bar equals to 0. So which implies that summation over xi equals to delta, and this is what we have to find here in the problem. So if we get such combination, and if that is giving 0, then we have the solution, and if we don't have, then we don't have the solution, and then again we will go back to the other combination of this xi. So this is the mathematical description of the naive approach, which one can use to find the element from an unstructured list. But if we see the performance of this classical search, or the, you can say, brute force, or we can say naive approach, so that will be the complexity, the time complexity will be order of n. So order of n, because we have to search the whole list, the whole database, to find that element. So here, for example, we have to search all the possible combinations. So let's say if we have binary, xi can belongs to 0 and 1, and we have n equals to, let's say, 5. So then we'll have 2 raised to 5 combination, that is 32. So we have to see all the 32 combinations. We may be we may be lucky that we may find, let's say, at the first evaluation, or the second, or the third, but overall we'll get this order of n time complexity, and n is basically m raised to n. So we have this exponential time complexity here. So exponential time complexity in m, not in n, but in m, because we have to see how many values the xi's can take. So yes, and then there are a few improvements that can be done to get that to improve. So if we use the classical computation in order to search an element in an unstructured list with probability half, so let's say if we just have a probability half to search an element, then we can reduce n by 2, but that will not give much significant decrement, because n by 2 is just, let's say, m by 2, and this is just like, let's say, 2 raised to n minus 1 something. So it's exponential, so we don't have any improvement. And the worst case, which we discussed, that if the element is at the end of the database, or at the last point of the list, then we have to traverse the whole n elements to find the solution. So there are a lot of classical algorithms that has been proposed here, which provide some increment on this order of exponential, this order of m raised to n. But we are not going to discuss those. And also there are other variant of this. So we are not going to discuss, but we are not going to discuss those classical algorithms. But yeah, just for the motivation part, that we have the unstructured list, and the naive approach doesn't do well. It has the exponential time complexity. So we'll see how this quantum algorithm for this problem solve this efficiently, or provide some improvement. So the bottleneck part in the last example, the mathematical description, we had this p of x bar equals to 0 that we have to see. And for this one, what we were doing is we kind of evaluating x bar. So we kind of evaluating for each x bar. So for each possible combination of x bar, we were evaluating this p of x bar. But let's say, can we compute this p of x bar for all value of this x bar at once? So I'm saying that, let's say we have this x1, x2 till x m raised to n, and then we feed it in a black box. So this is some black box. We don't know anything about this. And then we can get, let's say, the solutions. What is the solutions? We get some solutions. Okay, p of x1 is 0 or non-zero, p of x2 is 0, non-zero. We get all at once. So can we do that? So the answer, if we go to the quantum, is yes. So we can use something known as superposition that we can use, and we can actually find the solution to all this, find the solution for all this possible combination of x bar at once. And this is what the Grover's algorithm starts with. So taking the superposition and evaluating all the things at once. So the Grover search algorithm is named uh, on this computer scientist, this Love Grover. He published this paper, Quantum Unstructured Search Algorithm, in 1996, and that provides complexity. This so quantum search algorithm, this Grover's algorithm, provides a quantum complexity of this order of root n. So let's say if your n is some m raised to n, then we have order of m raised to n by 2. So yeah, it's not even much, but it's good. It's good enough. If we see in it's called quadratic speed up. It's not exponentially speed up, but it's quadratic speed up, and this one is quite good improvement for an unstructured search where there is no order or there is no structure in the list. And here we can see here, let's say, consider a list of million elements. So let's just take an example here. So list of million elements which contains integer 1 to 10 raised to 6 in some randomized order, and we need to traverse the list to find out the integer 59. This is just like a we can say with toy example, just to emphasize the meaning of this root n. So classically, if we see, so 10 raised to 6, so this one is again naive approach. So 10 raised to 6 by 2, so we have 5 into 10 raised to 5. So it's huge. It's almost like a million units of time, so zero point 0.5 millions unit of time. But when we do the quantum, so we have 10 raised to 6, we got 1000. So this one is 1000 units of time, this one is 0 0.5 millions. So there is a huge increment in terms of n here. So here n is equals to 10 raised to 6. So still the quadratic speed up is really good. So we have a huge improvement from 10 raised to 6 to 10 raised to 3. We have a significant improvement. And because of this square root, we have this quadratic speed up. This is not exponentially speed up like Shor's algorithm. And yeah, the question here arises that the question which arises here, that we are evaluating all the possible combinations of this x bar at once. So why we have this time complexity of order of root and not just order of 1? Because we are evaluating all the things at once, so we should get just order of 1, and it's like exponentially speed up. Just you perform this black box and then you have the result. So this is actually a good point, that we have the superposition and we are evaluating and we are getting all the solutions at once, but why we are not having the exponentially speed up? The answer is lies in the quantum thing, the superposition again. You So when we have the solutions, all the solutions, but we can't access that. So if we want to access that, then we have to collapse and just see the particular value. So we can't do the measurement. So what we have to do, we have to somehow see that, let's say if this one is the solution, x, some x I bar, this one is the solution, and we get here 1. Then if we want to perform the measurement, we should only get this part. not this one, not any others. So this is the main uh, point that actually brings down the exponential speed up to this quadratic speed up, because we can't access all the solutions in the which is actually a super which is actually in the quantum state in a superposition form, so we can't access that. Where we want to access only which is having one solution as one. So if we want to access that, we have to somehow increase the probability of observing that, and then if when we perform the measurement, we'll get only the xi bar. So that brings the quantum this exponential speed up to the quadratic speed up, and we'll see how we are doing this process and how we are doing this process. This one is actually known as probability amplification. So this one is probability amplification. We do some manipulations and we try to bring the probability of observing xi bar to almost 1, and then when we perform the measurement, we will with quite a good percentage, we will observe only xi bar, not the other ones. So yeah, this one is, so the other name of this probability amplification is the amplitude amplification. So either we can say probability amplification or amplitude amplification. So this is the main fundamental thing which is involved in this Grover's algorithm. So the whole Grover's algorithm basically relies on this amplitude amplification or probability amplification concept. So let's understand this. What is this amplitude amplification? So we have this set of n items, so from 0 to n minus 1, and these are actually the basis for the n-dimensional Hilbert space. So we assume these are the basis of n-dimensional Hilbert space, and the solution. So we have again the problem Px, and we assume the x naught, which belongs to this set S, is the solution of this problem P of x. So the probability amplification or the amplitude amplification, what we do, the step 0 is, this one is also known as preparation. So what we do, we create a superposition of all these elements here. We create a uniform superposition of all the elements that is present in S. So this one, so we have this x from 0 to n minus 1, and the since it's uniform, so probability of observing each of the element is 1 by n. So probability is 1 by n. Now after this step 0, we have two main steps that is contained in this that's the part of this amplitude amplification. The first one is flipping the sign of the x naught. So flipping the sign of the x naught means here, let's say for example, we have 1 by root 2, 0 plus 1. This is the uniform superposition of s equals to 0, 1. So we create a uniform superposition, and let's say we want only 1. So then what we'll do, we'll flip the sign of the 1. So flipping the sign means we just replace plus with the minus, and that will that will be the first step, flipping the sign of x naught, and here the x naught is 1. So we will get this thing. Now the second part is the inversion about mean. So inversion about mean, so we'll take the mean of amplitude. So mean of amplitude, and then we'll invert. So then we will invert amplitude about mean of amplitude. So we'll first in the second process, inversion about the mean, we'll first compute the mean of the amplitude, and then we'll flip all the amplitude about the mean of amplitudes which we have just found out. So now let's understand this two steps and also the step zero, the preparation state, for some examples. So we have this n equals to 3 qubit system, quantum system. So we have the n, that is number of possible combinations that can be, that we can have, is 8, that is 2 raised to n. So here all the possible combinations. So this one is the binary representation and this one is the decimal representation. So here, so for the step zero, which is preparation, so we'll create the uniform superposition of all the possible combinations. So we have all the possible combinations 0 0 t, all 0 to till all 1, and we have the amplitude 1 by root 8 because n is equals to 8, and this is what we have, we will get if we try to plot the amplitude. So 1 by root 8 is something around 0.3 um, 0.3635 something, yeah, 35 or 36 something. So that will be all the amplitude. So we have the uniform superposition and this one is the psi. So this is the psi. Now we will do the flipping of the sign. So this one is the step 1. So flipping the sign across, we can add across x-axis. So we have the solution. So x naught we have assumed here. Yeah, so let assume we have x naught which is equals to 0 1 0. So we will assume the x naught as 0 1 0. So we are looking for this part. So this is the first step which we had discussed here, that we perform the p of x and we'll get all the solutions at once. So this is what we have created all the in a superposition state, and then we'll perform something and then we'll get the solution. But now we have to amplify the probability that when we perform the measurement, because we can't access the amplitude of a quantum state, so we have to perform measurement and we have to see. So to perform the measurement and observe only this solution 0 1 0, we have to increase the probability of observing this 0 1 0 somehow. So that's what we are doing here. So the first step is again flipping the sign. So we flip the sign of this. So here it was, let's say, around it was around some 0.36. So here it will be minus 0.36. So we had just flipped the sign. We have not done anything extra here. Then what we will do, we'll compute the mean of the amplitude. So this one is the mean of amplitude. Mean of amplitudes. And note that we compute the mean of these amplitudes after doing the inversion. So we have the inversion here, 0 1 0 in the blue stick. So we, after doing the inversion, flipping the sign, we will find the amplitude. We'll find the mean of the amplitudes. So that's why we have the mean of amplitudes here as a dotted line, and which is less than the amplitude of all the other elements, because we have one element which is negative. So that's why it brings the mean downward, because here we can see this mean is a straight line which is passing through all the all the heads of this blue ticks. So that's how, because we have all the amplitude as a say, all the amplitudes are same, so that's why mean is also same as the amplitude. But here when we in do the flipping the sign, then mean got reduced. And now what we'll do is we'll find the inversion about mean. So inversion about means mean, so we will do the inversion about the mean. So we'll, for the example here, let's say 1 0 0. So we'll take the mirror image around the mean. So the mirror image, let's say this distance is x. So now this is all this. So if we take the mirror image around this invert this mean line, so we'll get something here, the blue thing, which is also has the same distance x, and this will be like the mirror image of the black dot. So that's called the inversion about mean. So if we, so earlier it was here, but now it went to here because we take the inversion about mean. So note that when we are taking the inversion about mean, so the probability amplitude is actually decreasing for all the other elements in the blue, in the black, as a which is represented in the black dots, except this required element, or the element which we want, This one is the blue. Because the blue is, we have this extra line here, and when we flip this, so this will go even farther, because we are not taking the inversion about this x-axis, but rather we are taking around this mean. So that's why this even go further, and we will have something like this. So in this way, we are kind of increasing now the probability amplitude, or the probability of this 0, 1, 0. So if we try to see what's the probability of observing this one 0, 1, 0, it's 78.12%, which we can clearly see from here, because it's more than 0.8. So more than 0.8, so it will be definitely more than 72%. So if we try to just calculate all these things mathematically, we will get the 78.12% of probability of observing this 0, 1, 0. It's good. It's good as compared to the other sticks here. So this one may have, let's say, this will be 0.04, so that will be like 4% kind of thing. So it's almost insignificant as compared to 78.2. But the 4% says that we can get sometimes this 000 or 001 also, or any other element also. So let's do this process again and see that how many times we can do this process, so that we can have a significant number of yeah, a very significant, almost, let's say, 99.9%, if we can achieve. So we'll come back to this one. Okay, so let's first go through how we can implement the flipping the sign, and then we will see more details about how we can increase the probability further from 78.12% to 99, or even further 99.9. So how we'll perform this flipping the sign thing? So flipping the sign, so let's say, so here I have used the f of x, but it should be p of x. So I'm just using this f and p interchangeably. So this f of px is equivalent to p of x bar. So will not get confused by this. It's just equivalent. I'm just using this interchangeably. So we have the solution x naught, and then this function will give 1, and then otherwise the function will not give 1. So the implementation of this flipping the sign that happens using this unitary uf, the f subscript f represents here flipping the sign, and it requires few ancilla qubits. So this is our data qubits. So data qubits. So let's say, for example, n equals to 3. We had this 0, 0, 0, and up to this 1, 1, 1. So x is basically some element of this set from 0, 0, 0 to 111. So x has 3 qubit data, and y is some ancilla qubit. So the unitary acts as follows. So we have this uf, and we have this data qubit plus some ancilla qubit, and the unitary acts on this set of qubits. Then it gives it outputs x, which is tensored with f of x plus y. So f of x plus y, and this one is again a simple XOR function. This is not this is a simple XOR function. So we'll take the we'll take the ancilla qubit as 0, -1 by √2, which is also known as this minus state. So if we perform this thing, so this is the implementation part now. So we have the ancilla qubit. So this one is ancilla, and we perform this unitary u of f. So we'll get this x, we'll get 1 by √2, this factor, and then 0 here. So 0, so this will be f of x. So this will be basically f of x plus 0, and this will be f of x plus 1. So f of x plus 0 is just simple f of x, and f of x plus 1 is f of x bar. So whatever we'll get, we'll just flip the sign. So we will just change it. So we have this, let's say, if of fx is 0, then f of x bar will be 1. So this is what it means. And then if we try to simplify for two conditions, that x is not equals to x naught, and for the solution x equals to x naught, what we will see, we will have the same thing here, x minus this state. So this will be x tensored with minus get state, and this will be minus of x tensored minus get state. So we got the same thing which we fed into the unitary, except the sign we have for we have a negative sign for x equals to x naught. So thus we can combine these two and we can write like this, minus 1 raised to f of x, x tensored x minus. So this will be minus 1 f of x, x tensored with minus. So when x is equals to x naught, this will give a minus sign, and minus 1 because this one is 1, and then we'll get this part. And if x is not equals to x naught, then we'll get this part. So this is how the flipping of sign is implemented using this unitary u of f. So now the inversion about mean. So how we can calculate, how we can actually find the this mean, and how we can do the inversion, that we have to see here. So yes, so we have this state, and let's say we have this state A or psi, whatever we can, and it has the amplitude. It is a uniform super. It's not a uniform superposition, but it's some superposition of xi's. So here, for example, this is not uniform superposition because alpha 3 is negative. So we can do, we have a state like this. So what we have to do, so we have to find the mean. So the mean is basically this thing, mu equals to 1 by n alpha I, and then we have to find the inversion. What's the value after inverting? So yes, so what we have to do is we have to kind of like do alpha. Let's say if we are doing it for alpha 1, so alpha 1 minus mu, so that will give you this distance, that will give us this distance alpha 1 minus mu, and then we have to subtract this thing from the mu itself. So this will become 2 mu minus alpha I. So this is what the height of, let's say here 0 1, so this will be the height of this part. So this is 2 mu minus alpha I, 2 mu minus alpha I, and the mu is basically just a simple mu is simple average, the average of the amplitude. And this this one is classical calculation. This can't be implemented here. This is just for the mathematical understanding, that how we have to find the this height here, and that can be found out by using this 2 mu minus alpha I. But for this we have to actually apply the unitary, and this is what the unitary is, 2 1 minus I. So this one is all ones. So this one is all ones unitary, and this one is identity. Only the diagonal elements uh, are one. So this one is unit, this one is identity, and this one is all ones matrix. So all ones matrix can actually be written as summation over xi and 1 by root n. So this will be all ones. So this will give us yeah, this will give us the one matrix. So 1 n cross n. And if we try to again simplify, then we can write this as 2 psi outer product with psi. So this psi is the uniform superposition, because we can take 1 by root n here also and 1 by root n here also, and then we can write as a psi 2 psi outer product with psi minus I. So this is what the unitary is for the implementation of this inversion about mean. So yeah, so we discussed this. So again, I will come to this part into more detail, the unitary operator for this part in more detail after discussing few things, and then we'll be able to understand even more about this inversion about mean. So yeah, so before discussing this implementation part, flipping the sign and inversion about mean, we were actually kind of seeing here that how we can increase the probability 78.12% to even further. So what we are doing here is let's go for the iteration 2. uh, we'll again do the same thing, the flipping the sign and inversion about the mean. So this one is inversion about mean, and we'll see how much we can get. So yeah, so we here we again did so earlier this was here somewhere, and then we did the flipping the sign. So we the this one, the blue, the head is coming down now with the same probability here, zero something more than minus 0.8 amplitude. And then we calculated the mean here. So mean is like farther down from here, farther down. It's way down from the this black tick, black dot, because we have a huge probability amplitude of this blue, so that is taking down the mean even down. And now we'll do the inversion about mean. So do the inversion about mean. So our this blue stick will go, is almost reaching 1 now. It's even it's like more than 9 something, more than 9, so it's greater than 0.9. And our other things, which when we invert, so they go towards negative, let's say minus 0.1 something. So if we try to calculate the probability of, if we perform the measurement here, and when we try to calculate the probability of observing 0.10, then we'll have this 94.53%. So earlier we had this 78.12%, now we have increased it to 94.53%. So now let's again do the same process. From iteration 2, we'll now go to iteration 3, and we'll again do the same process, flipping the sign and inversion about mean, and then we'll see what we can get. So again, we'll do the flipping of the sign. So flipping of the sign we'll do, and this 010, it will again come negative. So this one is again greater than, sorry, less than minus 0.9. And we calculate the mean. So mean is now in the negative side, and when we do the inversion about mean, so then we get the blue take here. But when we calculate the probability of observing this 010, this one is 33.01%. So we got 78.12% to 94%, and then we got 33%. So we have a huge reduction here, even less than the 78.12%. So this actually, this is because the reason why we have the huge reduction 94 to 33, because here earlier here when we did this flipping of the sign, all this black sticks, they come into the negative side. But when we go did when we went for this iteration 3, this is negative and the mean is giving the negative. So if we take the inversion about mean, then we are losing this probability a lot. We are losing this. So we are losing the twice of this actually, because when we'll flip, so this part will get lost and this part will be here. So we are losing a huge, say, area here. So it's almost like 0.2 and 0.2. So 0.4 kind of amplitude we are reducing. So that's why we have a huge reduction. So this actually tells us that we can't perform these steps forever and say that okay, we can assume we can get the 99.9% of probability for observing this solution 010. There should be some stop limit, and this is what is it is given here. So we have a performance limit, the upper bound, which is on the number of iterations, and that is upper bounded by this pi by 4 times under root n by m. So here n is the dimension of search space. So we have the n is here 8, and we have the number of solutions of the px or f of x, whatever we can say, m. So m is 1 here, so we have only root 8. So if we try to calculate the whole thing, so this will gives you 2 for n equals to 8. For n equals to 8 and m equals to 1, we'll get something around 2. So we have to decide, we have to keep some criteria, and we have to stop at somewhere, because we can't do this forever. And this will not give you, if we try to run this flipping of the sign and inversion about mean forever, then we'll not get good probability. It will again, so this will again reduce to, let's say, 12 or 12, and then this may again increase to, let's say, 50. This will again increase to 95, then this will go to 30. So this loop will continue forever. There will be like no significant of doing that. So that's why we have this order of under root n by m. And if we just simply say, then this one is order of root n. So here, so from here the time complexity of Grover's algorithms came. So this order of root n, so root n is coming because we have to perform the amplitude amplification part for under square root of n times. So let's go back to our simple thing here. So we said that we have this black box, we performed this. So this black box is just this what we have, this flipping of the sign here, we can say. This black box is performing this, and then we are trying to perform the measurement. So for measurement, we were doing here this probability amplification part. And so these things here, what we are doing is we have the solutions here, and then we are performing Grover's probability amplification for order of n times, and then we are getting finally xi bar. So that's why, so this one is order of n times, so that's why we have this complexity. Yeah, so that's why we have this complexity order of n. This part is order of 1, we just perform at once, but when we try to see the outcome, we have to perform this grow the probability amplification for order of root n times. So I'll go through the proof how we got this order of root n, and the more description or the detailed description is given in this chapter 6 of Nielsen and Chuang. It's very well written there also, how we can get this order of root n, the actual geometric interpretation, but I will also discuss here. So yeah, this one completes the theory part of this probability amplification or the amplitude amplification. That is the heart of the Grover's algorithm. And now we'll see how we can implement all this step, flipping the sign, inversion about the mean, in using the Grover's using the quantum gates or circuits. So what we have seen is, we have seen the motivation part, we have seen the amplitude amplification thing. So we have seen this amplitude amplification, then we have seen the theoretical implementation of this. Theoretical implementation of step 1, sorry, step 0 also, step 1 also, and step 2 also. We saw that all three. And now we'll proceed for the circuit implementation, how we can implement all these functions, which is we found here in step 1, step 0, and step 2, using the quantum gates. So yeah, let's again, we have the same thing. We have this such a space 0, 1 till n minus 1. Here the solution x naught, which belongs to the search space, and we have the problem p of x, or we can say f of x also. So we have this some black box, that is Grover circuit. We have the 0 thing, the state, the quantum state, which is given to us. We have the problem, we have the search space, and we found that we need to find the solution. Yeah, so let's start. So this one is I said that this one is probability or amplitude amplification circuit. Yeah, so here it's written, this one is the amplitude amplification circuit, and what we have to do is we have to perform this amplitude amplification in order of root n number of times. And this one is, this black thing is basically the p of x. So we are performing all the possible combinations, we are evaluating in one go, we can say, so something like that. So yeah, so we have some ancilla qubits here, we have the data qubits here. So the step 0, so the first step 0 is we have to create a uniform superposition of all the quantum possible bases, all the bases of the set S. So we have this S, which contains all the bases. So we have to create first the superposition, uniform superposition of all the elements in the such space S. So how we can do that? We can do using the Hadamard gate. So recall that a Hadamard gate, if we apply the 0 to Hadamard gate, it gives you this plus state, which can be written as the uniform superposition of 0 and 1. So similarly, if we extend this to 0 tensor n, so we have this h tensor n, and if we apply to 0 tensor n, so h tensor n is just, you have this h time n times, and 0 is similarly 0 tensor n times. So this will be h0 and the outcome tensor n. So if we try to simplify this thing, it's very easy to evaluate. It's very easy to just find out that if when h tensor n applied acts on 0 tensor n, then we'll have a uniform superposition of all the basis element from 0 to n minus 1. So for example, here when we had this 3 qubits, we have n equals to 8. So we created, the h will act on the 0 tensor 3, and then we'll get the uniform superposition of all the seven possible basis element of the such space of these 3 qubits. Now we will go to the first part of the amplitude amplification circuit. So we are breaking down this G. So now we are inside this G. So inside this G, we have this flipping of the sign thing first. So we have the data qubits here, n data qubits. We have Oracle workspace. So we can say that this one is just ancilla. This is nothing but the ancilla. And then how this oracles works. So we saw that the oracles is, if someone gave us to this x, then what it will give, it will give minus 1 raised to f of x x. And the f of x which we had defined here is like this. So if you have the solutions, if you have the solution 0 1 0, then we'll get the 1. And if we have anything else, then 0 1 0, then we'll get 0. So here when f of x will be 1, so this will have minus x, and then f of x will be 0, then we'll have x. So we'll only flip for x naught. Will not flip for x not equals to x naught. So this is how these oracles work. And its problem is specific. So we had to design the oracle or the circuits, the exact circuit using this quantum gates when we have the solution and we need to find which one is we know where we have to know which one is the solution here. Now comes the inversion about mean part. So inversion about mean, so we have to understand this, what's that. So the inversion about mean thing can be implemented by something known as diffusion operator. So this whole circuit which is inside this red box is known as the diffusion operator, and which is known as this D. So D is h tensor n to 0 outer product 0 minus and then h. So we got, but what we saw is, we saw this thing in the previous slides. So we saw this part that the inversion about mean can have, so has a theoretical representation of two psi's outer product with psi minus I, where psi is this uniform superposition. And how we got this, we got, so we computed the mean mu, and then we say, okay, this distance is x, this should also be x, this one is mu. So you found this the height here, this part will be 2 mu minus some alpha I. So that's why we have something here 2, this is kind of mu, and when alpha I will act here, so this will be our alpha I. So that's how we got this 2 psi outer product is psi minus I. Now how we can get this part from this 2 psi minus I. So let's go and see, let's see that how we can get that. So we have this 2 psi outer product with psi minus I, and that actually came from this part 2 1 minus I. So this is again all one operator, this one matrix, and this one is identity matrix. So we'll try to expand that. So we have this 1 by root n. Yeah, we just expand, written it in two terms, 1 by root n and 1 by root n. We have this 1, which is a column vector, 1 which is a row vector, and these two things when we'll multiply, so this will give us all ones matrix, and this is what we have here 1. So I'm just decomposing it. and then minus I, identity operator. So these vector actually can be written down using, can be actually constructed using Hadamard acting on the zero. So this one is actually 0 tensor n, and this one is also 0 tensor n. So just for the sake of brevity, I'm not writing tensor n, but this one is 0 tensor n because H tensor n acts on that to prepare the uniform superposition of all the states. So that's why I just replace this part as H tensor n and this part as H tensor n acting from the left. Yeah, acting from the left on this bra 0, and this one is H tensor n acting from the right. Yeah, I think this one is acting from the left, and this one is acting from the right. So this one is acting from the left on this get 0, and this one is acting from the right from on this bra 0 minus I. So but here also we can see that I can be written as H tensor n, H tensor n. The reason why, because H is I. So if we take H tensor n, H tensor n, we multiply it, we'll get the I tensor n. So this is also I tensor n. So yeah, we wrote now like this. So 2H tensor n, 0, 0, H tensor n minus H tensor n multiplied with H tensor n. And when we are taking this H tensor n common from both the right and the left hand side, we have the H tensor n, and then do 2, 0, outer product of the 0 minus I. So this is what we have after simplifying this diffusion operator, finding this diffusion operator from this 2 psi outer product with psi minus I. So this is kind of like theory thing, but when we have to implement this, we have to develop in terms of some circuit, we have to develop in terms of some quantum gates. So yeah, again we'll come back here. So we have so what we got here is, so we have this H tensor n and then 2, 0, 0 minus I H tensor n. So we have this H tensor n circuit, and we have this phase. So this thing actually can be implemented by just this part here. So if we have a 0, we don't add any phase, but when we have x, we'll add a phase of minus half. And why we are doing that? So let's see why we are having this kind of thing. So let's say or something acts on this. So this is what we have, the middle unitary. So we have 2, 0, outer product 0 minus I. Let's say if we act something act on this, so it acts on something, some state. So that state can have anything, 0, 1, 2, 3, 4, anything. So this will be 2, 0, 0 with x minus x. So if x equals to 0, so then we can say we get this one as 1, and 2, 0 minus 0 is 0. So we get 0 state. But let's say if x is not equals to 0, this thing is 0 because our inner product of 0 with other entry is 0 because they all are orthogonal. So 2, 0 minus something, some x is minus of x. So that's why we have this kind of interpretation here. So to implement 2, 0 outer product with 0 minus I, that if we get the 0, we'll just keep the 0. If we get x, then we'll just flip it. We will give an extra phase of minus. And then again, so this one will act here. So this one is this H tensor n, then this will act, we'll have this, then this will act, which is this, the H tensor n. So this is the whole diffusion circuit, diffusion circuit or diffusion operator, which is D, which is known as H tensor n, 2 outer product 0 minus I H tensor n. So this, with this we actually completed this the algorithm part here, and the circuit implementation. Now I will go through the geometric visualization of the proof of this. So that I think that will not take a lot of times. It's just 3 slides, and then we'll go to the circuit implementation and we'll quickly go through that. Sorry, the example, the cascade implementation. So here what we have is the we will try to see why the order is coming order of so why we have the complexity order of root n by m. So we'll try to just quickly go through that. So here we define the uniform superposition here. So let's say we have a n, which is the number of elements in the list, and f is the m is the number of solutions to the f of x. So we have this uniform superposition psi, which is 1 over root n summation over x, and then this x, and x is all possible combinations. So we will write x belongs to 0, 1, 10 third n. So we'll write like that. So we are now splitting psi into two parts. The first part which contains the solutions, all the solutions, and the second part which doesn't contain the solutions. So since we have m solutions, so the beta which is contains all the solution, so this one is solution vector and this one is non-solution vector. So we divided into two parts. The first part which contains all the solution, so it has the normalization factor 1 by root m because we have m number of solutions, and then the non-solution will have the normalization factor of 1 by under root n minus m because we have m solutions, so we'll subtract m from the n and then we get this n minus m. So yeah, so we have the psi, which is this uniform superposition we wrote in terms of alpha and beta. So alpha is normalized separately, beta is normalized separately, but then we have to again uh, so to normalize alpha and beta, so we have to need this 1 by root n minus m. So that's why it's multiplied and divide. So the division will go inside the alpha and we'll have this under root square root n minus m by n square root m by n. So this has some form of this cos theta and sine theta. So because here we can clearly see if we assume sine theta is under a square root m by n and sine cos theta as an square root n minus m by n, then we'll get this sine square theta plus cos square theta equals to 1. And that is basically because n minus m by n plus m by n, which is n by n, which is equals to 1. So that's why we can assume that we can do the some change of variables, and we can write like this. So this can be pictorially represented like this here. So here also note that that alpha and beta are kind of orthogonal. So we have a solution vector here beta and here alpha. So orthogonal because so here we can also clearly see that alpha and beta are orthogonal because all these are the basis elements. So if we take the outer product of this one with inner product of this one with this one, then definitely we'll get 0 because all are the bases. So we have just combined all the solution bases to beta and non-solution bases to alpha, and this psi vector will be something here, so this will be the psi, and it has an angle of, so if we try to see the angle here, so this one is theta and this part is, yeah, this part is cos theta and this part is the vertical part is sine theta. So this is the pictorial or the graphical representation of this psi state based on the solution and the non-solution axis. So in the probability amplification, what we were trying to do is we were trying to somehow bring this psi to this one, bring the psi to this one, almost like near to this beta. We were trying to do this part uh, after some probability number, some number of probability amplifications. We were trying to bring this psi to this psi prime. So we'll see how these things are actually going on, how this two steps flipping of the sign and the inversion about mean is taking place here in terms of this pictorial representation. Yes, so we have these things cos theta, sin theta, and whatever we have. So the first step what we had is the flipping of the sign. So flipping of the sign. So flipping of the sign means here that so if we perform the flipping of the sign, so let's say UF on the psi, what we should get is we should get cos theta alpha minus sine theta beta. Why we have minus here? Because flipping the sign means that whenever we find the solution, we flip the sign of the amplitude. So we have all the solution in beta, so we flip the sign of all the solutions here in the beta, so that's why we have this minus sign up before this beta. So how we'll represent this psi bar? Let's say psi prime. So psi prime will be somewhere here. So it has a positive, um, this one is again theta. So it has a positive component here in with respect to alpha, but it has a negative component with respect to beta. And this will be our psi prime. So this is after the first step. Now let's go to the second step. So we have the second step as step. So yes, so we have this state which is from the previous slide. So the second step is step 2 is basically inversion about mean, and we do the inversion about mean using this diffusion operator D, and that is basically this 2 psi with psi minus I. So here if we see that this psi 1 is actually coming from the step 1, the flipping of the sign. And now what we have to do is we have to take the inversion about mean, and that can be actually seen here as, so when we have this psi here, so the mean is something of that sort, we can assume. So now we have to flip this psi 1 with respect to this psi now. So earlier we have here, so let me erase this few things. Yeah, so earlier we have this theta angle, and then we did the flipping of the sign thing. Then we came here. So this will be our first step. This was our second step. Sorry, this one is our zero step. This one was our first step. And then what we'll do is we'll do the flipping about this mean. So this one is zero steps, so the mean. So earlier we flipped around this axis, but now we'll flip around this thing, theta, sorry, psi. So we have total angle here 2 theta, and when we'll flip around this psi, so we'll have a 2 theta angle from this side. So this will be 2 theta angle. If we compute from the alpha axis, then we have the total angle is 3 theta. And the remaining angle is pi by 2 minus 3 theta. So what we are observing here is, so we are observing that so we are going towards this finding the order of root m by n, n by m. By observing here is that we have to do first the inversion about this axis alpha, the second about this mean thing, that is psi, and we still got only 3 theta. The remaining is pi by 2 minus 3 theta. So we will see that how many rotations is needed, how many rotations are needed so that we can cover the remaining pi by 2 minus 3 theta. Before that, just to point here is, so we have a total rotation of 3 theta angle. So if we combine all this step, the first step and the second step here, we'll get a rotation operator, which is this. So this will give us, so this is a rotation operator. So generally, if we try to find a rotation with alpha angle, then the rotation operator generally takes a form of cos alpha minus sine alpha, sorry, sine alpha cos alpha. So here alpha we have 3 theta, so that's why we put the 3 theta, and we have the rotation operator as g. So yes, so here after first iteration, so we have 3 theta, so psi is g, psi prime is g. So if we if we perform the g, so g is this part, the g is this thing, the rotation, and if we perform this thing for let's say k times, so we'll get this form. This is what property of rotation operator we can say, This is what the property of a rotation operator, and this can be easily seen. It's not very uh, hard to understand this part. It's quite understandable. So here, yeah, I think here I missed something. So this one is, yeah. So this takes this form g raised to k. So this one is like a property in which we can easily see using the property that cos a plus b equals to cos b minus sin a sin b, and the other property sin a plus sin b, which is equals to sin a cos b plus cos a sin b. So we can use this property and we can find this g raised to k will take this form. So yeah, so let's see. Let's now finally conclude this topic by calculating why do we have this order of root n by m. So we have the psi and we have a theta angle here, and then we perform this flipping the sign. So that will be this O, and we got this thing. And then we performed the diffusion operator. This is D. So we perform the step 2 D. So we'll get this yellow line. Then we again perform the flipping of the sign. So this will compute our first iteration. So this will be our first iteration completed. Yeah, so here g1 hai. There is like g1, so we completed the first iteration, and then we again flip this. So we have a total angle here 3. So we'll again flip this, so we'll get 3 theta here. And then again, if we do the inversion about mean, so dog, so this will be flipping inversion, and then we'll get this g2, the second iteration, and that will have a total angle of 5 theta. So with respect to, so what we can see here is that in every iteration, that psi is moving closer to beta by an angle of 2 theta. So we have an increment of 2 theta. So this one is also an increment of 2 theta. This one was also the increment of 2 theta. So for every iteration, we are getting closer to beta by angle of 2 theta. So let's say we required k number of iterations to reach the beta. So we have this k times 2 theta kind of increment we have for every iteration, and theta is some initial angles. This one is initial angle of psi, some initial angle of psi. And what we want total angle to be pi by 2, because if we shift and take the initial angle into account, then we finally have to reach somewhat closer to the pi by 2. And all these things are with respect to axis alpha. So if we simplify these things, so we'll get this pi by 2 minus theta by 2 theta. And here, what we have an assumption here is that sine theta is very, it's so here we will assume that theta is less than, is very small. It's, sorry, theta is kind of like 0 degree. It's very small, and that can be understand because we have a huge list, but we have very small number of solutions. So that we can safely assume it's yeah, that we can safely assume. So now what we are writing here is we are writing sine theta equals to root m by n as inverse form. So sine inverse theta is sine inverse root m by n, and then we are kind of approximating because square root m by n is very small when m is less than equals to n, very small than n. So we'll get this pi by 2 minus square root of m by n by 2 pi and square root m by n. And if we try to simplify this thing, so we will get pi by 2 pi by 4 square root n by m minus half. And this will be basically the ceiling of pi by 4 square root of n by m, and this will give us order root of n by m. And this is how we prove that um, yeah, this is how we prove that we got this order of the complexity order of is square root of n by m. Yes. So yeah, so this completes the whole thing of the Grover's algorithm, and maybe we'll just wait for 2-3 minutes, and then we'll go to the Qiskit implementation of the Grover's algorithm. Okay, so we'll go through now the Qiskit implementation part. So I'll share the screen. So we'll quickly see the two examples here. The first one is the 2-qubit, and the second one is the 3-qubit for this Grover's algorithm. And we'll try to see how to implement the flipping of the sign and the inversion about mean, those two operations, and whatever we discussed in the circuit thing and the other part. So yeah, we start with so we here is just the importing of the libraries as we do all in the other algorithms or other quantum operations. So now we have this 2-qubit Grover's oracle. So here what we have is we have the solution as 0 1, and we have other possibles as 0 0, 1 0, and 1 1. So we created a unitary here. So the unitary will say that okay, 0 or 0 will pass as the same. We found that 0 1 is what we want, so we flip the sign here, and then we have 1, then we have 1. So we flip the sign when we find this 0 1. So that this can be understood something as flipping the sign thing. So so here we print the u. So how this u operator looks like. So yeah, again the same thing. We have the -1 here, only the second one, which is 0 1, which we want. So we have now this 2 for Q2 qubit. We initialize the two quantum bits, and then we have to perform at the end. We have to perform the measurement. So that's why we have this classical register, two classical registers. Then we added this unitary, which we have defined here, u. This one is actually decomposing of this big unitary which we have defined. The big unitary, this 4x4 unitary, and this is the decomposition of that. And this one is actually taken from this paper, the 4x4 decomposition of a 4x4 unitary as a CNOT gates and 1-qubit unitary. So we don't have to go into the details of this part. We can just assume, okay, we have the decomposition of this bigger unitary. And yes, so we are kind of checking here that u is unitary. So this flipping of the sign operation which we have defined using this u, it has to be unitary, because in quantum thing every operation can be performed only if it's a unitary. So the evolution is termed as the unitary evolution. So we are checking this unitary if the u is unitary, which we have defined. So yeah, it's true. We have the unitary. We have that u unitary. So now we are constructing the Grover's algorithm circuit. So let me go here and then we'll go see. So we have this step 0, which is the creating the uniform superposition of 2-qubit state. So we apply the Hadamard gate on each of the qubits. So this will be H tensor 2, and this will create a uniform superposition of all the 4 states 0 0 0 1 1 0 1 1. Now we apply this unitary thing 0 1, and this one is the flipping of the sign thing. So after this, what we will get is we will get 0 0 minus 0 1 plus 1 0 plus 1 1. So this unitary will only give minus phase to the required element, that is 0 1. This thing, the Hadamard and the X and the C naught, this thing is actually what we say the diffusion operator, the whole diffusion operator. This one is the Hadamard. So if we try to recall the circuit which we had in the diffusion operator, so we had this Hadamard H tensor n, then we have this 2 0 outer product with 0 minus I, and then we have this Hadamard operation. So this Hadamard is the n thing, H tensor n, H tensor n, and this X X H C naught H X X. This actually comes if we try to simplify this one comes as 0 2 outer product 2 0 outer product with 0 minus I. And yes, so this is the diffusion operator for the whole circuit. So we only applied here one iteration of the qubit circuit, Grover circuit. We have not applied much. We just have applied one, and then we can perform the measurement to see what we get. So if we try to simulate this one, then we can see here that we are getting 0 1 only with probability 1. So this is working very good for 2-qubit, only one iteration, because if we try to compute this order of n by m thing, so we have n equals to 4, and n equals to 4, and so we have a total thing is upper ceiling of pi by 4 and square root n by m. If we compute, that will come up as around let's say 0.9, sorry, that will come around like 1 point something, 1.8, 1.9. So if we take the ceiling and less than equals to, then only one iteration will be sufficient to get the 0 1 with high probability, with almost sure. So that's why we have this 0 1 with surety that we are getting, and this one is what we had the solution. So yes, that's working. Now we are going to this 3 qubit part. So the 3 qubit part, but here we have another twist. So we are not just only finding the 101, we are also finding 110. So we have a function and whose solution is 2, who has two solution. The first one is 101, the second one is 110. So till now in the examples also we saw only one solution, but here we have two solutions. So we define the unitary similarly we did as we did above. So we have this unitary, and this is kind of like flipping of the sign. So flipping of sign, we can say, and here we can say that 101 and 110 has only negative thing. Otherwise, except these two, all has only one element in, or only one. So this means when u3 will act on a state, then on a superposition state, uniform superposition state, then all the remaining things will remain as it is. Only the required element or the desired element will change its phase from plus to minus. So yeah, again we are creating this circuit, we are decomposing this circuit, this unitary, into other forms, and this can be done again by using this paper, and that is given as a function here in the cascade q circuit decompose. Again we are checking the unitary, whether u is unitary or not, but we can clearly see here the u is unitary because it's a diagonal matrix and it's quite simple. So, and if we want to check the u is unitary or not, we just have to check that u dagger u is equals to I. So we have to check that. And since all are diagonal, so, and dagger is also u, so here u dagger is equals to u. So which implies that u is square, which is equals to I. So now we'll construct the circuit for this 3 qubit system. So we'll have again the uniform superposition, flipping of the sign, then we have Hadamard, then we have Hadamard here, and then we have this X. So again the diffusion circuit. So diffusion circuit will remain the same. It's looking almost the same, except that we have added now an extra X here instead of the 2 which we had in the last case. So we have this Hadamard transform, we have this Hadamard transform, and this X within the X box, within this X and the C naught and H, all this terms has a phase thing, which we saw that when we have the 0, we'll keep the 0 as it is, but when we have the X, we'll add a minus phase to that, and then we perform the measurement on these 3 qubits. So what we expect that what result we expect is we should get probability 0.5 and 0.5 kind of thing for both the solutions. So this is what we have. So with probability 0.5, we have 101, we have 110. Now again, we may wonder that why we have only one iteration that is working when we had the 3 qubit case, but we saw in the slide that for the 3 qubit case, we actually we need 2 iteration at least, that will give us 94.12 probability, 94.12 kind of we can say 94.12 percentage of observing. But but there we are needing 2 iteration, but why we are needing here only why only 1 iteration? This is because we have now the number of solutions 2. Earlier in the slides we have number of solutions only 1. So if we compute this order of so let me write here. So we have a complexity of pi by 4, and then some square root of n by m. So earlier case, so we have this pi by 4, and then we have this square root of n is 8 here, and m is 2, so we'll get 4. And this is similar to what we have for the 2-qubit case. 2-qubit case with one solution. So that's why we need only one iteration, similar to what we have in the 2-qubit case with one solution. So we only need one iteration. But if we try to change the iteration, we can play with this circuit again. We can change the number of solutions here just by giving -1 or +1 to any of these. We can just change and we can play with that and try to see what kind of what are the problems we are getting here. So if we change to, let's say, 3 solutions, we only need one, but we can get all the 3. But if we reduce the number of solutions to only one, then we'll get the other we'll get these one of these as high, 94.12%. The other will also have some kind of significance, some kind of probability also associated with them. So yeah, so that's all I have. And yes, so we have few minutes left. So if anyone wants to discuss anything, I would be happy to do that. And if not, then we can end we can end the meeting, and I will share the slides and this notebook, the Grover's algorithm notebook.
No doubt, sir. Thanks you. Thank you.
Okay. So I will share on the Discord channel both the slides and that. Okay.
Okay. Okay. Okay. Thank you.
Okay. Thank you.